Good morning. We will begin today the last chapter of the course, namely the chapter on Legendre equations. And just like the Bessel functions chapter, we will start with a motivating example, namely a typical boundary value problem which leads to a Sturm-Liouville problem of a different type, namely the Legendre equation, named by the name of the mathematician who studied it. So take the time to write this down. More or less, we're going to go over these sections, basically. So remember, like in the previous topics, we're not going to go over every single section in the chapter. And even within the section, some of the parts will be skipped. So after we go over the lecture, check the sections and maybe do the examples similar to the ones I do in the class. And also read what I did in the class as well in the lecture, and don't read or skip over the part that I don't cover in the video lecture. The framework of this chapter should be familiar to you already. So once because it's going to follow the same script as with the Bessel functions chapter. So once we motivate the this equation and show how it pops up in boundary value problems, then we're going to take some time to figure out how to find the solutions of this equation, some properties of the solution, some computation rules, and so on. And at this point, make sure you print the Legendre equation handout. There's a similar handout on Blackboard as the one given for Bessel functions. So make sure you print that out or have it in front of you from now on, because that handout contains a summary of all the properties you need on this chapter. So let's get back to the main idea on which types of problems lead to the Legendre equation. So the typical textbook example is a steady state temperature in spherical coordinates. So let's suppose the object is a full sphere. Let's say the radius is between 0 and c. We're going to worry actually about the domain and the boundary conditions later, but for now let's just look at a full sphere as the object of study. And then let's say the heat propagates along the, the temperature of the object at a given point depends on the radius and the spherical coordinates, the radius and the two angles. Phi is the polar angles and theta is the angle measured with the z-axis. So let's label these axes first. So this is x, y, and z. So remember, in spherical coordinates, I should put here time t as well. So if you have a heat equation in spherical coordinates, u depends on the space coordinates. Spherical coordinates are theta and phi, and then the time t. So remember what all of these variables denote, right? So r obviously is the radius, the distance from the origin to the point on the sphere. And phi, remember, is the angle made by the projection of the point on the sphere over the xy plane with a positive semi-axis. So this is phi. Phi is basically like the polar angle, right? So measured counterclockwise with respect to the positive semi-axis. So in general, for a full sphere, once you establish the radius, the maximum domain, so for a full sphere, the domain for phi is 0 and 2 pi, because you go all the way around the center with respect to the xy plane. And then theta is the angle measured with the positive z semi-axis. So theta is between 0 and pi. Okay, so I hope it's clear, because phi goes all the way around. Theta, as you know, the maximum domain for theta that you can take is 0, 180 degrees. That covers the full sphere, right? So theta goes from 0 to 180 degrees, and then because phi goes all the way around 0 to pi, that covers the entire sphere. So that's the reason why you don't have a larger domain for theta. So please keep this in mind. This is basically the maximum domain in spherical coordinates. I'm calling it maximum domain because in some other problems you may have only a portion of the sphere. Let's say the object is a hemisphere, or maybe a quarter of a sphere, depending on the situation. So in that case, the domain for theta will be smaller than 0 and pi. But this is the maximum domain. So for a full sphere, this is the domain for theta. Okay, so what's the steady state temperature? Well, you assume that in the long run, the temperature stabilizes with respect to the time t, which means that if the temperature stabilizes, then the temperature depends only on the space coordinates. Furthermore, to simplify the problem further, because remember in this class, we will study PDEs only depending on two variables. Let's assume for simplicity that at the steady state, basically, or in general, the temperature depends only on two space coordinates, namely r and theta. So throughout this chapter, we assume that the temperature depends only on the radius and the angle made with respect to the z-axis. And if it's a steady state problem, of course, it doesn't depend on time anymore because you assume that the temperature stabilizes as t goes to infinity. So another point I want to make is that the Laplacian in spherical coordinates has various forms. You can look back when we introduced this Laplacian, or we can look in the book. There are various forms which are equivalent to this, but this is the one we're going to start with. So remember, it has a more complicated format, but in general, if u depends on all space coordinates, this is the Laplacian in spherical coordinates. So a typical heat equation, of course, has the format ut equals times the Laplacian, some constant times the Laplacian, and the steady state equation that gives you the steady state temperature is this simply the Laplacian set equal to 0, right? Because you assume that ut goes to 0. All right, so pay attention here. Once we assume that u depends on r and theta only, this middle guy is going to be dropped, right? Because it won't depend on phi anymore. And so therefore the steady state temperature equation, so the steady state PDE under this hypothesis is given by 1 over r times u partial r twice, plus the last term, 1 over r squared sine theta, and quantity sine theta u partial theta, and together partial theta one more time. So we can smell already that this will lead probably to a more complicated equation simply because of this more complicated format of the Laplacian. So remember, r times u, which depends on r on theta, partial r twice sine u theta, partial theta, and then together another derivative with respect to theta. And I should basically assume, just because we're going to have continuity assumptions, so let's actually impose a strict inequality in the domain here so that this makes sense. Again, when you worry about the division to 0, the whole point is basically to ensure that the solution is continuous at the boundary points. And that will basically constitute our boundary conditions. I mean, among other conditions, continuity is always a default boundary condition in this case. Okay, so this is the problem, how we approach it via separation of variables. So I mean, remember the starting point is always the same. Let's try to solve it via separation of variables. It's a linear PDE, homogeneous so far, right? I mean, we don't have other terms that don't depend on u. Let's see if we can separate it in a product form. So just like before, we're going to assume that the dependent variable is the product of a function in little r and a function in theta. Let's call the function in theta big H, again, to keep ourselves in agreement with the notation in the book as well. All right, so you should maybe try on your own to plug it in and see what you get when you do the separation variable. So maybe you can pause the video and then check to see if you get the same thing. By the way, when I say pause the video and try to do it, really it's a strong encouragement. Don't just take it as optional, because again, it's very useful if you do as much of these computations on your own as well as you follow along. If you just watch and not write on the paper, it's not going to work, as I mentioned before. All right, so yeah, let's plug in this format for u. So my equation now becomes 1 over r, little r, big R of little r, h of theta, and we're going to do partial r on the outside. And then sine of theta, here I'm going to have partial theta of big R times h. And then again, partial theta, what's left. So what I'm going to do on the next step, I'm going to replace partials with prime notation when there is no risk of confusion. So let me illustrate what I'm talking about here. So notice in the first part here, h of theta doesn't depend on r, so it can be moved outside of the derivative. But then what's left is going to be a second derivative with respect to r of a function that depends on r only. So at that moment, I can use the prime notation because there's no confusion, right? I mean, it's going to be just derivative with respect to r. So move the h of theta out. And on the inside, I'm going to have little r, big R of little r, double prime. And we're going to do something similar on the second term. Here I can move the r outside. Here it's partial theta. R with respect to little r doesn't depend on theta. I can move it out. And what's left, I can use the prime notation. Sine of theta, h prime of theta, and the product of the two, again, differentiated. All right, so obviously we can separate the two, and let's do another little simplification here so that I don't have this over r. Let's multiply both sides by r squared so that I can clear r squared from this denominator. So r squared times 1 over r becomes r h of theta, little r, big R, double prime, plus 1 over sine of theta, r squared cancels, and copy the rest. So the right hand side is still 0 because again it's steady state problem, right? Okay, so what's next? Well, separation, right? Let's move this guy to the right and then introduce the separation constant. So I'm gonna have basically, let's see if we could do it in one setting. If not, we're gonna do it on the next page. But yeah, let's do one more step. Let's move this to the right hand side and then separate. So we're gonna have 1 over sine of theta, big R, equals minus r h of theta, little r times big R twice prime. And now separation of variables. So I'm going to put the r on the left side. So we're going to have minus r and this quantity divided by big R here. All right, so that's what I'm going to write on the left side. So minus r, quantity r, little r, big R of r, over big R. We're going to write it again on the next page. And on the right hand side, 1 over sine of theta, h prime of theta, prime over h of theta. Okay, so let's double check. big R 1 over sine and this, there it is, minus R little r big R double prime H, there it is. Okay, so this is the separation of variables in spherical coordinates, and again we're going to introduce just like before a separation constant, which is going to end up being positive. We'll see why that's the case, and so that's why it's convenient again to denote it by minus lambda. So with that, let's actually continue on the next part. And we're going to start with this separation, and then we're going to analyze the two equations that we end up with. So stay tuned for the second part.